Okay, this is lesson 6.5, and in this lesson we're going to solve problems involving quadratic equations. This is going to be a two-part lesson because there's 4 examples we're going to work through. We're going to do the first 2 examples in part 1 and the second 2 examples in part 2. When you're asked to solve a quadratic equation, we've worked through option 2 and 3 where we factor to solve, and option 3 where we use the quadratic formula to solve. That was our last video lesson. But we could also solve by graphing. If we could produce a graph, we could just look on the graph and read off our answers. But the goal is we need to understand when we can use each of the different methods. So we're going to work through a few examples, and we're going to look at a couple of the methods and discuss why we used each method. So let's get started with a model of the path of a toy rocket. The formula h equals -1/2 gt squared plus v naught t plus h naught, the little 0 means naught, which means initial, can be used to model the height of a projectile, where g is the acceleration due to gravity, which is 9.6 on Earth, and v naught is the initial velocity in meters per second. H naught is the initial height. So this is an actual formula that can be used to model the height of a projectile. Projectile is like something thrown or shot that flies through the air and eventually lands due to gravity. First, we're going to create a model, which means we're going to make an equation for a toy rocket that's launched upward at 60 meters per second from the top of a 3-meter platform. So we're going to use this equation, and we're going to plug in the pieces of information that were given in the question. Well, we're given this 60 meters per second and 3 meters. The 60 meters per second is the initial velocity. So this is our v naught. And since it's launched from the top of a platform, this is our h naught. And we're given this 9.6 meters per second, which is our g. So we're going to fill in our equation with this information. We got -1/2, g is 9.6, and we've got t squared, plus v naught t is 60 meters per second, so 60t, plus h naught is 3. So we can do a little simplifying here. We can multiply these two numbers, and we end up with the equation -4.9 t squared plus 60t plus 3. And now we have an equation to model the height of our rocket. So let's use our equation to answer a couple questions. B, how long would the rocket take to fall to Earth? Round to the nearest hundredth of a second. So that implies our answer is going to be a time. So we're going to solve for t. And we know that because it says how long. How long implies a t. So we want to find t. Fall to Earth also tells us something. That tells us what height we're talking about. Earth would be ground level. So that would be a height of 0. So we're finding t when the height's 0. So we're just going to use our equation to do that. Here's my equation. We want height 0. So we have 0 equals -4.9 t squared plus 60t plus 3. So to solve, we either have to graph this, factor it, or use the quadratic formula. Something in standard form, to graph it, is actually quite challenging. We'd have to first find the x-intercepts, which is basically what we're doing to solve for t anyway, so we're probably not going to graph this. Factoring, well, we'd be looking for numbers that multiply to -4.9 times 3, whatever that is, and add to 60. As soon as you have decimals, factoring probably goes out the window. So that leaves us with one option, the quadratic formula. So we're going to use the quadratic formula. Our quadratic formula is x equals -b plus or minus the square root of b squared minus 4ac divided by 2a. And our equation has an a, a b, and a c. A is negative 4.9, B is 60, and C is 3. Now, what's neat about the quadratic formula is it's set up to solve for x. But we're not working with x's in our equation, we're working with t's. So when we use the quadratic formula for this purpose, we're going to say t equals, because we're solving for times. And now we can just fill in the b's, the a's, and the c's. And we get something that looks like this. 4.9, nope, made a mistake. Not 4.9. Negative b, so negative 60. Plus or minus the square root of 60 squared minus 4 times negative 4.9 times 3. And that whole thing is divided by 2 times negative 4.9. Now we have to do a little bit of math. We're going to simplify what's under the square root, so we're going to find that discriminant, which tells us how many answers we're going to get. We learned that in the last video. 2 times negative 4.9, well, that's just negative 9.8. I found a mistake. Not a big one. The acceleration due to gravity is not 9.6. It's 9.8. It doesn't change much, except for right here. I actually did the multiply by half correctly, so we are working with the right number. I don't know why I wrote the example wrong. Whatever, mistakes happen. All right, let's figure out that discriminant. Square root of something. Well, let's find out what it is. So this is going to tell us how many answers we're going to get. So 60 squared minus 4. So we get 60 squared minus 4 bracket negative 4.9. Two negatives, we're going to get a positive. We're going to have a positive discriminant times 3. We get 3,658.8. That discriminant's positive, we're going to end up with 2 different answers. So let's figure out what the 2 answers are. T and T. Probably going to end up having to round. How do we get the 2 answers? Well, I'm going to show you how to be efficient with your calculator now. We already have this written out. We have a plus minus. So we're going to write the equation once with a plus, and then we're just going to go change it to a negative to get our second answer. So it'll look like this. I'm going to build a fraction. If you don't have a fraction button, just put the whole top in brackets and then divide. I've got negative 60 plus the square root of 3658.8 divided by negative 9.8. When we get negative 0.049, I can round to 5. So our first answer is negative 0.05 seconds. And now instead of hitting clear, we're just going to go back and edit. And we're going to change that plus to a minus. Hit equals, and we get our second answer, 12.3. So now the question is, what's our answer? How long would it take the rocket to fall to Earth? Well, our experiment doesn't start in negative time. It starts at 0 and from an initial height. And then it goes and it lands over here at 12.3. So the answer is 12.3 seconds. So we'd say, therefore, the rocket takes 12.3 seconds to fall to Earth. Now notice this dashed part of the parabola. That's the part that would go back to the negative 0.05. This would be our 12.3. This part of the parabola is not actually part of the rocket launch. It's the unused part or unneeded part of the parabola. This part really doesn't exist because this is the negative time region. We're only working in positive time because time can only go forward. So we're starting at an initial height of 3. We're launching up into the air. We're falling to Earth at 12.3 seconds. That's how we can interpret our answer. All right, let's try the next question. What's the maximum height of the rocket rounded to the nearest meter? So we're asked now to find the maximum. And what's nice is we have a way to find the maximum, because if we understand what maximum means, we can find it. Maximum implies vertex. The vertex has two parts. It has a x part and a y part, but in this case it has a time and a height. We want the maximum height, so we want the y part of the vertex. So how do we get the vertex? Well, we could complete the square and find the vertex, starting from standard form, or we could use something we found in the last example. We found the x-intercepts. When you have the x-intercepts, you can find the axis of symmetry by adding the x-intercepts and dividing by 2. That would be this t. Once you find a t, put it in your equation to find a height, and you've got your answer. So let's do that. Let's find our t by taking our two x-intercepts, or t-intercepts, adding them and dividing by 2. If we do that, we get 6.12 seconds. And now we just have to use our equation to find the height. Height is negative 4.9 t squared plus 60t plus 3. And we're going to use our 6.12. So the nice thing about an equation is if you know the x, you can find the y. In this case, if we know the t, we can find the h. So now I'm just going to type this in my calculator. We've got negative 4.9 bracket 6.12 squared plus 60 bracket 6.12 plus 3. And we get 186.67, we'll just call it 7. It says round to the nearest meter, so 187 meters. And there we have it. The maximum height is 187 meters. Again, we could have completed the square on this. We just would have had to work with decimals and it would have been a little ugly, but we could have done it and we would have ended up with the same vertex. All right, let's try our last part, D. Over what time interval is the height of the toy rocket greater than 150 meters? Over what time interval? Ah, neat. So it wants times. And we're given a height. So we want to find time when we have a certain height. So we just have to use our equation and solve it. Well, if we forget, our equation is negative 4.9 t squared plus 60t plus 3. And this time we're given the height, 150. And the question is solve this, because we want to find the times. If we find times of like 1 and 4, it says from 1 second to 4 seconds, we would be between 150. Because 1 and 4 would be when the rocket's at 150. So let's solve it. Well, how do you solve? Well, to solve, we need it to say 0 equals. So we can do that by moving the 150 to the other side. Makes negative 150, add 3, we get negative 147. Now what? Well, now we're just solving like we did in the first example. Not first example, in part B. We could try to factor this, but again, factoring might not be possible because we have decimals. So our real only option is to use the quadratic formula. And we've got A, B, and C. So let's use the quadratic formula. If we forget, the quadratic formula is t equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So let's fill that in. I'm going to work up here. T equals negative b, so negative 60, plus or minus square root of 60 squared minus 4 times a times c. All over 2a. So the only thing that really changed about this is this last number. Everything else was the same from the last time we did it. So we got negative 60 plus or minus negative 9.8 on the bottom, and we want to find out what that discriminant is. Let's see how many answers we're going to get. So we got 60 squared minus 4, negative 4.9, negative 147. And we get 718.8. So now we can try to get our two answers. We're going to get a first time and a second time. And since we have decimals, we're probably going to get approximate answers. We want round to the nearest hundredth of a second, so 2 decimal places. So let's give it a shot. We're going to type it in first with the plus sign. So we've got negative 60 plus the square root of 718.8 over negative 9.8. We get 3.386, so we'll call it 3.39 seconds. And now instead of retyping, we're just going to go back in here, and we're going to change that plus to a minus. And we get 8.86 seconds. And these two times are when the parabola would be over a height of 150. So just draw you a little sketch here. We know our parabola starts at 3 meters. We know it lands at 12.6 seconds. And we know the maximum is at 6.12 seconds. And the maximum height on the last page was, I've already forgotten, 187. So that'll be here. So we want to know when it's over 150. So that's somewhere here. So we want to know when it's over here. Well, our parabola goes up, goes to the maximum, falls back down, and then hits 0. So we want to know this time and this time. Well, we just found it. These times are 3.39 and 8.86. So we just found that in between those two times, our parabola is over 150. So we can conclude, therefore, the rocket is over 150 meters between 3.39 seconds and 8.86 seconds. If it said how long, we just subtract and we get an answer like 5.5. All right, that's it for part D. We're going to do one more example about the width of a path, and then we're going to wrap up part 1. A rectangular park measures 100 meters by 60 meters. A path of constant width is to be paved around the perimeter. The mayor wants to be sure the path does not reduce the area of grass by more than 10%. What is the maximum allowable width of the path rounded to the nearest tenth of a meter? Well, this is a little bit of a tricky question. Let's try to draw a diagram. So we have a rectangular park that's 100 by 60. And the area of this park would be, well, length times width, which is 100 times 60, which would be 6,000 meters squared. So we can only reduce it by 10%, which means we'll only have 90% of our area. So that's 0.9 of our area, which would be 5400. So we can only have that much. Because what we're going to do is we're going to take some of this field and we're going to put a path around it. So we're chopping some off on every side, and it's going to be the same width. So here and here, here and here, here and here, here and here, it's all going to be some width. We don't know what, we're going to solve for it, but we know that whatever we're left with in the middle needs to be 5,400 meters squared, because we're chopping some off to make the path. So we want to find the W that gives an area of 5,400 meters squared. That's what the question is. So how do we do that? Well, we need to find the area of this space. How do we do that? Well, area is just length times width. So let's look at our length. Our length was 100, but we chopped off a little bit of W here and a little bit of W here. So 2 W's we took off. So that means our length is now, instead of 100, we took off 2 W's. And our width was 60, but we took off a W and we took off another W. So our width is now 60 minus 2W. And what do we know? Well, we know that the area that we need is 5400. So now we have an equation. Oops. And all we need to do is solve the equation. Now, the hardest part of this example is getting it all set up, taking all that information out of the question, using a diagram to figure out how we're going to write an equation for area. That's the trickiest part. Now that we're at this point, we just need to solve it. Well, how do we solve? Well, we expand, collect like terms, move everything to one side, and see if we can solve it. Well, let's take a look. 5400. Let's FOIL this out. 100 times 60 is 6,000. 100 times negative 2W is negative 200W. Negative 2W times 60 is negative 120W. And negative 2 times negative 2 is 4W and squared. Now collect like terms. 4W squared we'll put first. Collect like terms in the middle. We got negative 320W and 6,000 on the end. Now we want that 540 over to the other side, so we have 0, because we always want 0 if we're trying to solve. And 6,000 minus 5,400 is 600. And now we have an equation. Now, we could use the quadratic formula, but since we don't have decimals, let's try to factor. First we have 4. Is 4 common to all these numbers? The answer is yes, so let's common factor first. We get w squared. Negative 320 divided by 4 is negative 80, and 600 divided by 4 is 150. So now the question is there something that multiplies to 150 and adds to negative 80? There is not that I can see, so we can't factor this. But what we can do is we can use the quadratic formula. Now we could use the quadratic formula here, or now that we have an even simpler equation, just right here, we can use the quadratic formula on that, and we'll get the same answers, but our numbers that we work with won't be as big. So now we use the quadratic formula. So let's do it. We're working with widths, so we're going to have w equals for our quadratic formula. And it's negative b to start, so negative 80, which would be 80 plus or minus the square root of b squared, so negative 80 squared minus 4 times a is 1 times c is 150. Now if you don't see the common factor, if you use the quadratic formula using an a of 4, a b of negative 320, and a c of 600, you'll get the same answer. So it's okay. And then we're going to divide by 2a, 2 times 1. So in the interest of time, I've done this discriminant in advance. I'm not going to show it on the calculator. It is 5,800. And we're going to divide by 2. And finally, let's find our w's. I've typed these in a couple times, so instead of typing this in, I'm just going to go straight to the answer. The two w's we get are 78.1 meters and 1.9 meters. So now we just have to think about this in context of the question. Can we have a width of 78.1 meters? Well, if this width is 78.1 and this width is 78.1, that's over 150 meters that we'd be taking off of just 60, which doesn't make any sense. So this number is too big. We reject that number. It's a math answer, but it's not a practical answer. 1.9 is much more practical. If we take off 1.9 here and 1.9 here, there's plenty of room for the field in the middle. Same with here. Take off 1.9 here and 1.9 here, there's over 96 meters left in the middle. So our answer is just this 1.9. So at the end, we can now conclude. Therefore, the maximum allowable width of the path is 1.9 meters. All right, so that's two fairly challenging applications of quadratics that we've just worked through. Temper your expectations for the second video. The questions aren't nearly as difficult in the second video. Try some practice questions around area and rocket launching, and I'll see you in part 2.